Hello, in this video, I am going to discuss Cambridge International AS Physics Paper 2, which is May June 2024, Paper 23. Let us get started. First question, the drag force Fd acting on a sphere falling through a liquid is given by Fd equals 6 pi eta, that is called eta, RV, where r is the radius of the sphere, v is the speed of the sphere in the liquid, and eta is a property of the liquid which we call it as viscosity. A show that the SI base units of viscosity are kilogram per meter per second. Now, how are you going to do this? Is that you have to compare, since the equation is an homogeneous equation that also satisfies that the left-hand side SI base units must be equal to right-hand side SI base units. Now, let me solve this. On the left-hand side, I have FD. Don't bother about whether it is FD, FA, FC, FZ. It doesn't matter. As long as it is a force. The unit of force, the SI base unit of force is kilogram meter per second square. F equals MA. M is measured in kilogram. A, acceleration, which is measured in meter per second square. Now, equals to the equation. I need the equation. 6 is just a number. Pi is a constant that has no unit. What about eta? So you have to find this viscosity, the unit of viscosity. R is the radius, so the SI base unit of radius is meter. V is the speed, so the SI base unit of speed is meter per second. Now I'm done with that, so I try to simplify. Kilogram meter per second square is equal to eta meter square second negative 1. Now you have to shift all the SI base unit to one side and left that viscosity on the other side. Now I have kilogram meter per second square divided by meter square per second, which is equal to eta. Now I continue from here. Eta is equal to kilogram. I just leave it. Meter, this is to the power of 1. And this meter square per meter square, I have to shift it up. When I shift out, the power of 2 becomes negative 2. So negative 2 is here. Or I write it again. This is meter per second square. And then I just shift out this meter square per second. This one will become meter per second. Meter negative 2, second to the power of 1. Now the unit of viscosity is kilogram. M, the power, remember multiplication, the power you have to add. S, negative 2 plus 1. Then you left behind. Kilogram meter, 1 plus negative 2, you get negative 1. Negative second, negative 2 plus 1, you get negative 1. Ta-da! Proven. Now B, the sphere has a radius of 3 cm and is falling vertically downwards at terminal velocity of 2 meters per second through the liquid. Drag force acting on the sphere is 0.096 Newton. Calculate the viscosity of the liquid. Since the drag force is being given, I rewrite the equation. Fd is equal to 6 pi. Let me see, 6 pi viscosity and RV. Viscosity and RV. Now, FD is given, which is 0.096 is equal to 6 pi. And the viscosity is not given because you have to calculate. R is given as 3 cm. But before that, I want you to see this unit of R and the unit of velocity. Velocity or terminal velocity is measured in meter per second. So that is why your radius, you have to change it to meter. So you divide by 100, which is equal to 0.03 meter, and times with the V, which is 2. So the viscosity is 0.096 divided by 6 pi, 0.03 times 2. Work it out. You should get 0.085 kilogram per meter per second. So 0.085 is the answer. Now see, the sphere is shown in Fig 1.1. On Fig 1.1, draw and label arrows to represent the direction of three forces acting on the sphere as it falls at terminal velocity through the liquid. Now, before I draw, you need to understand the definition of terminal velocity. Definition of terminal velocity means that it is the maximum velocity achieved by this sphere when all the forces acting on the sphere is balanced. So that also means that the resultant force acting on the sphere is equal to zero. There are three forces acting on this sphere. How do I know? The question mentioned it. First one is definitely the weight of the sphere, because sphere has mass, definitely it is falling, it has weight. So the weight must act at the center of gravity of the sphere. Remember that. So from the center of the sphere all the way down, draw this, put this as weight, label this as weight. And what about the other two forces? Now, remember the question told us about viscosity. So this sphere experiences a drag force. Remember that? So the drag force, viscosity, acting on a moving object. Resistance by the liquid is called viscosity. And at the same time, since the liquid, since the sphere is being displaced in the liquid, so there is also another force which we call it as buoyant force or upthrust force that could only act when object is being displaced in fluid, either liquid or gas. So the upthrust force is here. Upthrust force. That's all. Now D, density of the liquid is 920 kilogram per meter cube. Show that the upthrust acting on the sphere is 1.0 Newton. Now, do you still remember the equation of upthrust? I put F up, which is equal to rho Vg, where rho represents the density of the liquid, V represents the volume of the sphere, and G represents the gravitational acceleration of the sphere. Density of the liquid is given, so we have no problem, 920. But the volume of a sphere, so you have to use a little bit of math here, which is 4/3 pi r cubed. Remember that? And times with your G. So now I sub in all the values. R is given, remember 3 cm, but you have got to change it to meter because you look at the equation of, you look at the unit of density, this is a meter. So you times 0.03, you cube it. And then times with 9.81. Upthrust force that I got was 1.021 Newton. You can round it off to 1 Newton. And after that, calculate the mass of the sphere. Mass of the sphere, I am going to use back the diagram, the arrows that I draw on the sphere. So there are three forces that are acting on the sphere, which balance each other because the resultant force acting on the sphere is equal to zero. Remember, the sphere is falling at terminal velocity. Now I'm going to form equation. So two outward forces balance the downward force, which is the weight. I'm going to put the drag force plus the upthrust force is equal to the weight of the sphere. How about that? The drag force is the one that I have for the drag force is the one that is being given, which is 0.096. Upthrust force, you just calculated in D part 1, which is I am going to use the intermediate value, which is 1.021 is equal to weight. I just calculate my weight first. So weight is equal to 0.096 plus 1.021. And I got 1.117. 1.117 Newton is the weight. But hey, do you should remember W is equal to mg, where m represents the mass, g represents the gravitational acceleration. Since I have the value of weight is equal to mass times 9.81. Mass is equal to 1.117 divided by 9.81. Let me do it. And my value is 0.114. I put it in terms of three significant figures. You can put it as 0.11, not a problem. Two significant figures is acceptable. So that is all about question number. Let us move to question number 2. Define displacement from a point. Remember, what is the difference between displacement and distance? Displacement, if you want to think it easy, is a shortcut. Shortcut from where? Shortcut from your original position, your starting point, to your end point. Just based on your starting point and your end point. Just draw a line joining starting point and end point. That is called displacement, right? Distance, which is long, long way, right? So I would define displacement. It is distance or distance move in a specific direction or given direction. Doesn't matter. B, an object is projected horizontally at a speed of 6 meters per second from a slope as shown in Fig 2.1. The slope is at an angle of theta to the horizontal. Air resistance is negligible. Oh, thank God. The object lands on the slope at a time of 0.71 second later and stops without rolling or bouncing. Wow, that is fascinating. First part, determine the horizontal distance traveled by the object. Now, for this one, I would like to resolve it into horizontal direction. You know how? Okay, horizontal distance is equal to horizontal velocity times with the time taken. The time taken is already been given. Now, horizontal velocity is 6 meters per second because they have already explained object moves at horizontal speed. Now, 6 times 0.71, and my answer is 4.26 meter. 4.26 meter is the answer. Determine the vertical distance traveled by the object. Now, to determine the vertical distance traveled by the object, you know what am I going to do now? I am going to redraw back the theta. So this is the theta, and then this is theta, and okay, just erase a bit. Okay, redraw back. Okay. I am drawing a right angle triangle. This is theta. Since they asked me to determine the vertical distance, and I have already calculated the horizontal distance, which is 4.26. This is called vertical. I put D distance. DV represents vertical distance. How about that? So, not going to solve that as well because I have two unknown. No problem. Just erase everything here, even though I have already calculated the distance. Still, I cannot find the vertical distance because I do not have the value of theta. I have lack of information to perform my calculation here. Therefore, I'm going to use back the equation that I used. Remember one of the kinematics equation, which is this one. Let me roll out a little bit, which is theta. Okay, this is the one. Let me show you. This is one of the very popular equation, kinematics equation. I'm going to use that. S equal ut plus half at squared. How about that? But since the object is moving downwards, right, going down, so I'm going to change that g, a to g. Oh, I am going to do, okay, but I have to resolve into vertical direction. So Sy equals Uyt plus half gt squared. Remember the question mentioned that these objects being projected horizontally. There is only horizontal velocity, initial velocity. There is no vertical initial velocity. So that is why the whole thing here is equal to 0. So vertical distance is equal to half, g is 9.81, and the t is given as 0.71, and I square it, and I got 2.47 meter. So 2.47 meter is my answer. Now, the third one, use your answers in B part 1 and B part 2 to calculate the theta. Since we have all the values, the vertical distance and the horizontal distance. Don't you think we can calculate our theta? Let me redraw the triangle right now. Okay, maybe this is a little bit small. I'm going to draw it larger. Horizontal, and then this is, okay, oops. Okay, never mind, make it, okay. Okay, this is nicer. So this is 90 degrees. This is my theta. Horizontal distance was the one that I calculated earlier, which is 4.26. Vertical distance was the one that I calculated just now, which is 2.7. Now, you are asked to find the theta. Use a little bit of math here. I use tangent theta. Tangent theta is equal to opposite 2.47 divided by 4.26. Theta is equal to shift tangent 2.47 divided by 4.26. And my theta is 30 degrees. 30 degrees is the answer. Now, part 4, determine the magnitude of the displacement of the object from its original position. Since you already have, remember what I told you about displacement, I need to redraw the triangle. Now, it is the same triangle. This is 4.26. Okay, starting point is here, remember, because with the speed of 6 meters per second, but I'm not going to label that speed. I don't want to confuse you. Just want to let you know this is a starting point. This is 2.47. So starting point is here. And then landing point is here. So displacement, remember, I told you earlier before I define displacement, I say it is about the starting point and the end point. Draw a line. This is called displacement. And when you look at my right angle triangle, it represents the hypotenuse of the right angle triangle. Again, recall your math. So the magnitude of the displacement, I put it as D, is equal to square root 2.47 square plus 4.26 square. And the answer is 4.92 meter. 4.92 meter is my answer. Now, part 5, by considering energy, you have to use energy, no choice. Calculate the speed of the object just before it lands. So the speed of the object, but before that, I'm going to use principle of conservation of energy, stated that the total initial energy is equal to the total final energy. Total initial energy, look at my right angle triangle, the one that I drew upwards here. This object is at its initial point, which is this one. I put it as A. It has a certain height, vertical height. Therefore, it needs to have gravitational potential energy. And remember, this object is projected at horizontal speed. Therefore, this object must have kinetic energy. And equal to final energy, which is kinetic energy just before it lands. Now I'm going to put mgh plus, that is the equation of gravitational potential energy. Kinetic energy is half mu x squared because it is projected in x direction, and equal to half mv squared. Now I don't need the mass of the object because I can just cancel them off. G is 9.81. H is 2.47. Remember, H is the height. Plus half U in terms of X direction, that is 6 squared, equal to half V squared. Work it up. Work it up. So I have 42.23 is equal to half V squared. V is equal to 42.23 times 2 and square root the answer. And I got 9.19 meter per second. So 9.19 meter per second is the speed just of the object just before it lands. Question number 3, state Hooke's law. Robert Hooke, not Captain Hook. Remember, Captain Hook is the bad guy. Now, Hooke's law states that extension of elastic material, yeah, is directly proportional to force applied, but everything must occur beneath limit of proportionality. So that's the answer. B, the variation of the applied force with the extension for a sample of a material is shown in Fig 3.1. This sample behaves elastically up to an extension of 80 millimeter and it breaks at point X. Now, first part, on the line in Fig 3.1, draw a cross to show the limit of proportionality and label this cross with letter P. Now, I have an easier way to determine the limit of proportionality. Remember how I define Hooke's law? Force is directly proportional to extension. Now, when you go into the examination hall, first of all, take out the ruler. So what are you supposed to do is that from origin, you draw a straight line to see where the straight line stop behaving like a straight line, right? So I'm going to draw. Okay, it is right here. So I am using the red color to draw. And I'm done with that. Keep my ruler. So you could see that it is stop behaving, right? As a straight line at, okay, this is 2, 4, 5. This is 5.2, 5.4, somewhere here, because this one start to curve already. So I will say, okay, at this point, right? So I put a cross there. Give me a while. Yeah, okay. Give me a while. I am going to put a cross here, and I label this as P. Now, okay, that is done for the first part. You have to make sure that this is 5.4. Just want to label this, right? And then on the line, second part, on the line in Fig 3.1, draw a cross to show the elastic limit. Label the cross, this cross with a letter E. Do you know what is elastic limit? Elastic limit is a point where beyond it, the object will either break or deform plastically. Now, the question already mentioned, this sample will behave elastically up to extension of 80 millimeter. So you search, which is 80 millimeter? This is it. So up from, yeah. So put a cross here, and then label this as E because up to that extension, that is the maximum extension. That's it. And C, the sample in B has a cross-sectional area. This is area. An initial 0.4 millimeter square and an initial length of 3.2 meter, that is L. For deformations within the limit of proportionality of the sample, determine the spring constant of the sample. Now, spring constant, I would like to use the graph, right? So from graph, F equals to Kx, remember? F equals Kx. So I just get a value, K is equal to F over X. Doesn't matter if you don't find the gradient of the graph, you just find the ratio of F to X. You know why? Because the graph starts from origin. So I take a value. So my value is the one that I label here, 5.4, and this is 60, right? Okay, this is 60. So I'm going to use that. Force is 5.4. Okay, K is equal to 5.4 Newton. And the extension is 60, but in millimeter. Remember, look at the unit of spring constant. It has to be meter. So 60 millimeter, you have to divide by 1,000 or you times 10 to the power negative 3. K value is 90 Newton per meter. So 90 Newton per meter. And the second part, the Young modulus of the material from which the sample is made. Since Young modulus is asked to determine, I'm going to use the equation of Young modulus. Y is equal to stress over strain. Now, stress is force over area. Divide strain is extension over original length. So you simplify this, becomes FL over AX. That is your Young modulus. I want you to see this. F over X. Don't you think this is a value of the spring constant? I am going to modify that. Young modulus is equal to spring constant length over area. Make my life easier. Young modulus is equal to spring constant is 90 because we are using the same spring. And the length is given as 3.2 meter. Going to put that 3.2 meter over area. Area is a problem now because area is given as 0.4 millimeter square. Remember, 1 millimeter, I'm going to write it here. 1 millimeter is equal to 1 over 1,000 meter. 1 millimeter square is equal to 1 over 1,000 meter. You have to square it, which is 1 millimeter square is equal to 1 times 10 to the power of negative 6 meter square. And 0.4 millimeter square is equal to 0.4 times 10 to the power negative 6 meter square. Don't ever make careless mistake because of this. I'm going to sub in that. This is 0.4 times 10 to the power negative 6. So your Young modulus is 7.2 times 10 to the power of 8 Pascal. 7.2 times 10 to the power of 8 Pascal. Now, part D. Okay, look at the question. Determine an estimate of the work done on the sample as it is extended from zero extension to its breaking point. Explain your reasoning. You know, when a graph is being given, there are two information that you could obtain from the graph. One is the gradient of the graph. Second is the area under the graph. In this case, I am going to use the area under the graph to give me the work done. That is why the question stated as estimation. So you have to estimate. So I'm going to erase this, the point here. Okay, and I am going to draw new lines here. Okay, make sure that how to determine the area under the graph. The problem is that some part of the graph is straight line, some part of the graph is curved. So how do we do about that? I am going to use different method right here because for curve, those who learn at math, right, you definitely know that you need to do integration to find the area under the curve, right? But the problem is some of our physics students are not taking F math. That is why they do not know how to do the integration. That is why integration is not included in our physics syllabus. So without integration, we have to do estimation. I would count the area under the straight line and the curve, right? So for this part, okay, I am going to find, okay, for this part, because it is just a straight line, so not a problem. This part is not our problem. Okay, we can find the area. Okay, but the other part, okay, I am going to make this, okay, draw up like this. This is 1, 2, 3, 4, 5 here. Okay, draw a line like that because as long as the box, okay, I want to calculate the box, but my box, right, I need to make it as small as possible, not very small, but not too big because the estimation will be not so accurate. So just nice, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So I'm going to draw boxes here. So this is one. This is another one. And then, okay, until this point over here. Okay, just draw a line. And horizontal as well. I'm going to use 5 boxes each. So this is 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And then 1, 2, 3, 4, 5. Okay, let me draw it right now. Like this. Like I okay. Like this. Oh, forgot to draw this part. Sorry. Like this. Like this. like this, as well as this one. You just draw it across here. And then thank you very much, ruler. I'll keep it. Oh, I forgot to draw a vertical line here. Okay, now let me draw the last vertical line here before I perform my calculation. Okay. This is the one. Now I'm done with that. So all I need to do now is just to calculate the number of boxes involved here. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, maybe 36 here, 37, 38, 39, 39.5 maybe, right? So I'm going to use that as 39.5 first boxes. Okay, 39.5 boxes times the area of one box, which is, one box is 20 millimeter. You have to change it to meter. So 20 times 10 to the power negative 3, and the height of one box is 1 Newton times 1. So I have here, and then plus with the area of triangle here. So half times 5.4 times 60. Half times 5.4 times 60 milli, remember? Half, okay, work. So my estimation would be 60, 5.4 times half, and here I got 0.162, and then here 39.5 times 20 times 10 to the power negative 3. Here I got 0. Oh, why is it so far away? So this is 0.79 plus 0.162. Let me erase that. Okay. Now plus 0.162. And my answer is 0.952. 0.952 joules. 0.952 joules is my answer. Now, answer given by the mark scheme is within 0.8 joules to 1.2 joules. So mine was within the range. Now, E, a second sample of the same material has a larger cross-sectional area. I highlight this. Larger cross-sectional area than the original sample, but the same initial length. Two samples are each deformed with the limit of proportionality. State and explain qualitatively, that means no calculation involved, how the spring constant of the second sample compares with that of the original sample. Now, how I'm going to do this is that I'm going to write down the equation that I used just now. Young modulus is equal to spring constant times length over area. Since the length, because they mentioned that the original same initial length, see here, right? Length is constant, but larger cross-sectional area. Young modulus is the same because same material, right? So Y is equal to KL over A. Y length are constant. Okay, I have to explain where Y is. Let me explain first. Where Y is young. Sorry, this is young modulus. K is a spring constant. L represents length, and A represents cross-sectional area. Now, okay, Y, L are constant, and A is directly proportional to K. See that? Because these are constant, you times out the A, you get A is directly proportional to K. Since A is larger, K will be larger. So that is how we discussed qualitatively. Next one, question number 4. A progressive transverse wave traveling from left to right as shown at an instant time in Fig 4.1. This is a wave. R and T are the points on the wave. A, state the phase difference between the points R and T. I want you to see this. This is one complete oscillation of the wave, right? So up to here, this is already 180 degrees. Now the difference between R and T here is 90 degrees because it is a quarter, right? So this is 90 degrees between R and T. So you just take 180 degrees plus 90 degrees, you get 270 degrees. Now, the next one. On Fig 4.1, draw an arrow at point T to show the direction of the movement of point T at instant show. I erase this first. When you are asked to show what happens to the vibration of point T, first of all, this is a transverse wave. The definition of transverse wave is that the vibration of particles R and T will be perpendicular to the direction of travel of the wave. Since the wave is traveling to the right, remember they told us that progressive wave is traveling from left to right. That means this wave is moving, wave profile is moving from left to right. R and T will be vibrating up and down. But whether R and T are moving up and down, we need a guide. Now, what is the guide? So I am going to draw another wave profile to show that this wave has already been shifted to the right because this wave is traveling to the right. So shift this a bit, shift this a bit, shift this a bit to the right, shift this a bit. So just until T. Now I am going to just sketch it. You could see that. Look at my red color wave profile, the new wave profile. New wave profile. Okay, something like this. It seems like the wave is shifted, the wave profile is shifted from black to red wave, moving to the right, right? So how do you determine the vibration of T? T, look at the position of T based on the new wave profile that I drew. So it has to go downwards. So the arrow is downwards. So you have to draw arrow downwards. That's the answer. Now the next one. See, the horizontal distance between R and T is 0.62 cm, as shown in Fig 4.2. The speed of the wave is 0.27 meter per second. Calculate the frequency of the wave. I am going to use V equal to F lambda to calculate the frequency of the wave. F is equal to V over lambda. V is given, not a problem. 0.27 is V. But lambda is a wavelength. It is not being given. Now, how do I do? This is one full wave. I split into 4 parts. I call this as 1 over 4 lambda, 1 over 4 lambda, and 1 over 4 lambda. So I get all together between R and T, I get 3 over 4 lambda. So 3 over 4 lambda is equal to 0.62 cm. Lambda is equal to 0.62 cm times 4 over 3. Lambda is equal to 0.827 cm. Now, look at the unit of speed. It is in meter, so you got to change your lambda to meter. So lambda is equal to, shift 2 points to the front. 1, 2, divide by 2. So 0.00827 meter. Sub in 0.00827. When you calculate, you should get 32.7 hertz as your frequency. 32.7 hertz is my answer. Now, part D. The wave is a water wave produced by a dipper S1 attached to a vibrator in a ripple tank. An identical dipper S2 is attached to the same vibrator. The two dippers produce an interference pattern on the water in the tank as shown in Fig 4.3. The wave crests from each source are represented by solid lines on Fig 4.3, and the wave troughs are represented by dashed lines. At point P in Fig 4.3, the wave from S1 has the same amplitude A as the wave from S2. Describe and explain the amplitude of the resultant wave at point P. Now, where is P? Oh, okay, P is here. It is the wave crest meeting with a wave trough. So I would say that from S1 is the wave trough, right? At P, okay, wave, okay, wave produced by deeper one is equal to a trough. I just put it first. Wave produced by S2, deeper 2 is a crest. Now, okay, which wave trough you put it as? Give me a while. This one I erase it. Wave trough, because they say they're of same amplitude, so I put negative A. And then wave crest, I put it as A. So the resultant displacement or amplitude at P is equal to A plus negative A, which is equal to 0. So, okay, I would say that waves from S1 and S2 superimpose at P at the same time, destructive interference occurs at P. That is why resultant displacement is equal to 0. The next one, question number 5, part 1, state Kirchhoff's second law. For Kirchhoff's second law, stated that in a closed loop, this is super duper important, total electromotive forces, or you put EMF, equals total potential differences. That's all. Second part, state the conservation law that gives rise to Kirchhoff's second law. Kirchhoff's second law is about the principle of conservation of energy. Principle of conservation of energy. That's Kirchhoff's second law. B, a circuit contains a cell of internal resistance R and two resistors of resistances R1 and R2 as shown in Fig 5.1. Potential difference PD across the two resistors is V. The current in the cell is I. Okay, fine. First part, use Kirchhoff's law to show that the total resistance RT of the circuit, external circuit, is given by that expression. I want you to see this. This is a current coming out from the EMF of a cell. This is what I call junction. I am going to use Kirchhoff's first law, right? This is a junction where the current will split out to I1 and this is I2. I would write that, right? Okay, now I stated here, junction. Okay, because if I stated that, I could ask the examiner to refer to Fig 5.2, right? By Kirchhoff's first law, okay, at a junction, refer Fig. You could ask the examiner to refer to Fig 5.1. I is equal to I1 plus I2 because I put some symbols of I. Now, Ohm's law, I is equal to V over R. That is why from here, V, I put V total over R total is equal to V1 over R1 plus V2 over R2. So for parallel circuit, V total is equal to V1 is equal to V2. That is why you can cancel off the V. You have 1 over R total is equal to 1 over R1 plus 1 over R2. Ta-da! That's it. Second part, the electromotive force, EMF, of the cell is 1.5 volt. When the values of R1 and R2 are 10 ohm and 15 ohm respectively, the PD measured by the voltmeter is 1.38 volt. Calculate the internal resistance R of the cell. I need to write down the equation of EMF. How about that? So EMF is equal to V plus IR. So this is called the potential difference across the internal resistance. This is the potential difference across R1 and R2. The problem is now I do not have the value of the current. So how do I do about this? Let me roll it up, scroll up to this diagram so that it's easier for you to see. And I'm going to label EMF given as 1.5, not important. Voltmeter reading is 1.38. That is very important. And I want you to see R1 and R2. They are being connected in parallel. So how do you find the total resistance across R1 and R2? I try to simplify the circuit. So I find the total resistance between R1 and R2. 1 over R total is equal to 1 over 10 plus 1 over 15. How do I know that? Because the question gave me, right? So R total is equal to 1 over 10 plus 1 over 15. You invert it. So from here, the R total between R1 and R2, you get 6 ohm. Now, simplify the circuit. So this circuit will become something like this. I draw it smaller. This is R. And then this is the battery. And then this is I, the big current. And then this one becomes 6 ohm because I have already combined the two resistances. Now, I need to find the value of I. How do I find the value of I? Voltmeter reading is being given as 1.38 volt. So I can use Ohm's law. V equals to IR. V is 1.38. I don't know. And R is 6 ohm. I is equal to 1.38 divided by 6. Now, okay, use your calculator to do this. You should get 0.23 ampere. So since I got the value of I can sub in everything here. EMF is given as 1.5. Voltmeter reading is 1.38 plus 0.23 R. R is equal to 1.5 minus 1.38 divided by 0.23. So the R value that I got was 0.52 ohm. 0.52 ohm is the answer. C, a third resistor is added in parallel with R1 and R2 in the circuit in Fig 5.1. State and explain the effect, if any, of this change on the current or in the cell. You know that if you face any difficulties in like getting the answer for this, I would strongly suggest you to use a method of, we call it as substitution. Remember just now I have already combined the total resistance of R1 and R2, which is 6 ohm. Yeah, I'm going to use that, right? Let's say a third resistor, this is R3, right? And I put the value of R3, maybe 10 ohm. Yeah, I want you to see the total resistance. What happened to the total resistance? Initially, this is about R1 and R2. Okay, R1 and R2, total resistance is 6 ohm because they are being connected in parallel. So added R3, R total becomes, okay, I'm going to do it now, 1 over 6 plus 1 over 10. And then you just invert it. I would want you to see the value decreases to 3.75 ohm. So the total resistance decreases when the third resistor is being connected in parallel with these two resistors. Don't you think so? When the total resistance decreases, I didn't change the battery is still the same, right? Therefore, the EMF of the battery is still the same, constant. In this case, we can use Ohm's law, right? So the current is inversely proportional to total resistance. Don't you think so? I would say that, okay, total resistance of circuit decreases But, okay, EMF is constant. Okay, just put EMF is constant. Ohm's law, I is inversely proportional to 1 over R. Okay, I is inversely proportional to R. That is why current increases. So current increases. What about the PD measured by voltmeter? Okay, now the PD measured by voltmeter, look at the battery. Okay, now this is the internal resistance. This is the battery. This is the EMF of the battery, which is constant. This is the total resistance, which is the one that is being decreased, 3.75, right? Decreases. The total PD, or the EMF of the cell, is equal to the PD across the total resistance between the three resistors plus PD across the internal resistance. Since the PD across the cell, the EMF of the cell is still constant, there's no change of that. The PD across the total resistance here, because resistance decreases, PD will have to decrease, right? So, or you can use this. No, you use this. Okay, I put V R. Now I change this. The total EMF is equal to the PD across all the R plus IR. See, the current across the internal resistance now increases due to the third resistor, right? So therefore, the PD across the internal resistance will have to increase. And the total PD is constant, the total EMF is constant. Therefore, the PD measured by voltmeter will have to decrease, right? So I say EMF is equal to V across R plus IR. Since current increases, the potential difference across internal resistance increases. Therefore, EMF constants. Hence, potential difference measured, or PD measured by the voltmeter. PD measured by the voltmeter, measured by voltmeter decreases. That's the answer. Now, question number 6. Nuclei of an isotope of samarium, Sm, each contains 62 protons and 85 neutrons. A, state the nuclide notation in the form AXZ for this isotope of samarium. So samarium, just put samarium here. And proton number is 62. Z represents a proton number. A represents the sum of proton and neutron number. So which give you 147. So just put 147 here. B, this isotope of samarium is radioactive and decays by emitting particles. Gamma radiation is not emitted. Good news. The energy spectrum of the emitted particles is shown in Fig 6.1. Now, the first part, explain how Fig 6.1 shows that this isotope of samarium emits alpha particles and does not emit beta particles. Do you know about beta particles? Beta particles are fast-moving electrons, and beta particles, because it is not just about fast-moving electrons, it is also about positrons. So electron and positrons, they have a range of speeds. So we would expect, if this is about beta particles, we would expect to see a range of kinetic energy, because after all, kinetic energy depends on speeds. Don't you think so? Half mv squared. So, but in this case, I noticed that the kinetic energy of the particle is static. It's the same. It's constant. Yeah, even though the number of the particles are increasing, right? So I'm going to explain using that. I said that the beta particles have a range of speeds. Hence, beta particles have a range of kinetic energies. Since kinetic energy is constant. when the number of particles is increasing, suggested that alpha particle with fixed kinetic energy being emitted. That's it. Second, the isotope of samarium decays to an isotope of neodymium, Nd, right? Forgive me if I pronounce it wrongly. Give the radioactive decay equation for this decay. Include the nucleon and proton numbers of all the particles involved. So samarium, first of all, 14762 decay, yeah, by emitting alpha particle. Alpha particle is 42 helium or 42 alpha, is up to you, plus Nd, neodymium. I don't know whether it's true or not. So how do I get the nucleon number of neodymium? You take 147 minus 4. So you should get 143 because nucleon numbers on the left-hand side must be balanced with the nucleon numbers on the right-hand side. So 143 plus 4 is equal to 147. What about the proton number? Proton number on the left-hand side must be balanced by the proton number on the right-hand side. 2 plus 60 is equal to 62. Ta-da, we are done. And see, a baryon is composed of 3 quarks, which all have different flavors. The baryon has a charge of 0. Oh, this is very important. The charge is 0. 2 of the quarks in the baryon are an up quark, which is, I would do this. That is a good habit, actually. That is the up quark, the charge of up quark, and the bottom quark, which is -1/3, the charge. Now, first part, determine in terms of the elementary charge E, the charge on the third quark in the baryon. Remember, baryon must give rise to 0 charge. So plus 2/3 minus 1/3. 2 minus 1, I still left 1/3. So I have to minus another, or I put it in bracket, minus another 1/3e. So in order for me to get the whole charge equal to 0. So this -1/e, I call it as strange. Okay, the charge is -1/3. Oh, don't put that. That's not the name. Okay, -1/3. -1/3. E has already been given, so I'm not going to write it now. State a possible flavor of the third quark in the baryon. I call it strange, very strange, right? So that is all for the discussion in this video. If you face any problem, do comment below. If you need the PDF answer for free, exactly free, just for you, comment below as well, right? See you in my next video. Bye.